Welcome. Today, we're diving into a fundamental concept in data preprocessing: normalization versus standardization. These techniques are crucial for preparing your data before feeding it into machine learning algorithms. They can significantly impact the performance and stability of your models. Understanding when and why to use each one is key. Let's uncover the distinct purposes and applications of these two powerful scaling methods. Raw data often comes with features measured on entirely different scales. Imagine a dataset where one feature represents a person's age, typically ranging from 0 to 100, while another feature represents their income, potentially ranging from thousands to millions. Without scaling, features with larger values might dominate the learning process, misleading algorithms that rely on distance metrics. This imbalance can lead to slower convergence or biased model outcomes. Normalization is a scaling technique that transforms features to a specific range, usually between 0 and 1. Its primary goal is to ensure that all features contribute equally to the model, preventing features with naturally larger values from having an undue influence. By squishing the data into a predefined boundary, normalization makes features comparable, regardless of their original units. It's often employed when your algorithm expects inputs within a certain interval. The most common form of normalization is min-max scaling. This method rescales a feature to a fixed range, typically 0 to 1. The formula for min-max scaling is x equals x minus x min over x underscore max minus x underscore min. Here, x is the original value, x underscore min is the minimum value of the feature, and x underscore max is the maximum value. This simple linear transformation ensures that the smallest value becomes 0, the largest becomes 1, and all other values fall proportionally in between. Normalization is particularly useful for algorithms that are sensitive to the magnitude of feature values. Examples include k-nearest neighbors, where distances between data points are crucial, or support vector machines, which might be influenced by larger feature ranges. Neural networks, especially those using activation functions like sigmoid or tan, also benefit significantly from normalized inputs, as it helps prevent issues like vanishing or exploding gradients during training. One major advantage of normalization is its ability to speed up the convergence of gradient descent-based algorithms. When features are on similar scales, the cost function's contours become more spherical, allowing gradient descent to find the minimum more directly and efficiently. It also ensures that all features are treated equally, preventing features with large values from disproportionately influencing distance calculations or weight updates in the model. However, normalization does have its drawbacks. A significant one is its sensitivity to outliers. Since min-max scaling uses the minimum and maximum values of the feature, a single extreme outlier can drastically distort the entire scaled range. If an outlier is present, the majority of your normal data points might get squished into a very narrow interval, effectively losing much of their distinction after normalization. Now, let's turn our attention to standardization. Standardization transforms data to have a mean of 0 and a standard deviation of 1. Unlike normalization, standardization does not bound values to a specific range. Instead, it reshapes the distribution of the features to resemble a standard normal distribution, making it particularly useful for algorithms that assume Gaussian distributed data. The core of standardization is the z-score transformation. For each feature, you subtract the mean of the feature and then divide by its standard deviation. The formula is x equals x minus mu over sigma. Here, x is the original value, mu is the mean of the feature, and sigma is the standard deviation. This process centers the data around 0 and scales it based on its spread, making all features have similar scales relative to their distribution. Standardization is generally preferred for algorithms that make assumptions about the distribution of your data, such as linear regression, logistic regression, and some forms of support vector machines. It's also beneficial for principal component analysis, where you want to ensure that all features contribute equally to the principal components, regardless of their original variance. Tree-based algorithms, however, are typically less affected by feature scaling. A key advantage of standardization over normalization is its robustness to outliers. Since standardization uses the mean and standard deviation, it's less prone to being skewed by outliers. This means that even with outliers, the relative distances between data points are better preserved, and the spread of the data remains more representative. Despite its advantages, standardization also has some limitations. One is that it does not scale data to a fixed range. While this provides robustness against outliers, it means that the transformed values can extend indefinitely in either positive or negative directions. This lack of an upper or lower bound can be an issue for algorithms or models that specifically require inputs within a strict, predefined range. The choice between normalization and standardization depends on your data and algorithm. If your data contains outliers, standardization is generally a safer bet because it's less susceptible to distortion. If your algorithm explicitly requires features to be within a certain range, such as 0 to 1, then normalization is the appropriate choice. Always consider the underlying assumptions of your model. In summary, both normalization and standardization are indispensable tools in a data scientist's toolkit. They address the critical issue of feature scaling, but they do so with different approaches and for different scenarios. Normalization scales data to a fixed range, while standardization transforms data to have a zero mean and unit variance. Selecting the right technique can drastically improve your model's performance and interpretability.